is Greg Pickett, obligatory company information, the company I operate under. Okay. Brief overview of today's talk. We'll start off with those nosy bastards out there. Next is all about packet normalization, or what we're really talking about, what we're trying to do here. Working it out, getting those normalizations designed, implemented into a POC, the putting it into practice, ID guard. And then finally finishing up for some challenges to implementing this in a production environment, as well as some concerns. So let's start off with those nosy bastards. As network defenders, we see scans and probes of our network every single day. From the inside and from the outside, everybody is targeting us. In fact, some of you actually may be out there targeting us. Identifying our assets, right? Now, how they do it. Network stack implementation is highly discretionary. Differences identify the operating system type and version, allowing attackers to identify their targets by matching the headers of their target to known operating system implementations. If your target has a time to live, or TTL, of 128, and uses the following options: maximum segment size, or MSS, of 1460, followed by a single Nmap, followed by Windows size 0, followed by 2 Nmaps, and ends in a selected ACK or ACK, then your target is likely a Windows 2003 server. Implications. If they identify your assets, they know the weaknesses and how to attack them successfully without triggering your sensors. Some of you may be familiar with this. All right, airport security. In the US, we have a very invasive group called the TSA that likes to get very personal with you when they're examining you. All right? So this is a good example of what happens on the network. All right? Seems to be a fact of life. But I began to think about this a bit and think, did it have to be? Did we have to just sit there and let them scan us day after day and just let them identify us and target us? So I said, it doesn't have to be. We can change that. Why can't we remove the differences, all right, to remove their advantage, strip them of their ability to fingerprint, to significantly reduce their chances of success? Now, my answer to this was packet normalization. All right. But the first question to ask is, okay, what exactly is packet normalization? It's not an entirely developed concept. There are many expressions, but most are incomplete, or what I call confused, and certainly nothing that carried out what I had in mind. I want to begin the discussion of normalization by differentiating normalization from scrubbing. Scrubbing is to do away with or to cancel. Normalization is to make normal, especially to cause to conform to a standard or norm. They are sometimes used interchangeably. However, I believe this is a mistake. Scrubbing, or removing parts, it doesn't move the packet toward a standard. It just makes it less of itself. To move a packet toward a standard, I believe you have to reorganize its structure, not unlike what is done in databases. Now, both of these sorts of approaches are seen in varying degrees, some in the same solution, illustrating the confusion that is out there. Start off scrubbing, used by a number of firewalls, OpenBSD as a PF module, the PFSense firewall, the NetFilter Linux firewall. There is a randomization of the IP ID, clearing of the IP do not fragment field. Also, depending on the solution and your configuration, it'll set the IP type of service, the differentiated services code point, which is what that kind of became, and the TTL. And there is some IP fragment reassembly. Primary concern of these solutions: policy violations, abnormal packets, and abnormal flows. scrubbing with some normalization, but not enough nor the right kind of normalization, nor effective in fingerprint prevention, nor practical, lacking the ability to cover the entire network. Now there are also scrubbing going on in a number of network devices, like the Cisco ACE and the Cisco ASA. They will randomize the TCP sequence number. They will clear the TCP reserved field, urge flag and urge pointer, clear some TCP options, and enforce a minimum IP TTL. Also, some fragment reassembly. Primary concern, again, is policy violations, abnormal packets, and abnormal flows. Scrubbing primarily with some normalization, but not enough normalization, nor the right kind of normalization. Right? Nor effective in fingerprint prevention, nor really practical, lacking the ability to cover, once again, the entire network. How about genuine solutions dedicated towards some sort of normalization or heavily involved in normalization? It brings us to the traditional device, the IPS IDS. They are doing a lot of IP fragment reassembly and doing some sanity checks on the detail to make sure there's no evasion going on. The primary concern, though, is detecting attacks and detecting evasions. Strictly normalization going on, but we're also seeing not enough, nor the right kind of normalization, not effective for fingerprint prevention, nor practical, once again, because it lacks the ability to cover the entire network. How about outgoing normalization? Something really interested in making sure the packets are uniform, meeting a standard, making them all look alike. Right? Not really. Right? Not really. Now, if you're going to go ahead and take a look at this as a problem, it's important to start with the fingerprinting process. This is obviously very simple summary of the fingerprinting process, starting with really Nmap. Nmap is the most popular, hence the title, Let's Screw with Nmap. Most popular, most common tool out there. But the techniques that it uses, right, its methodology is pretty much common. This is this general overall process that fingerprinting tools or tools that have fingerprinting modules go through to identify targets. Right? TCP, UDP, and ICMP probes are sent. The responses are collected. They're compiled into a fingerprint, kind of a shorthand. And this fingerprint is then compared against a database of known or previously enumerated operating systems. By matching the fingerprint to this database, it then identifies that operating system with some degree of certainty, depending upon how close that matches. If it has an 8% match, it's 80% confident that the target is indeed running X operating system. Now, where to start with this process? Obvious place is once again at the Nmap fingerprint database. I don't know, has anyone here looked at the Nmap fingerprint database before? It's extremely complex. Not very fun to look at. Right? So, given the complexity, I didn't believe it was a good idea, right? It's not a good idea to try to unwrap that giant monster of a database. But what about other fingerprinting tools like Xprobe? It's old, but it's out there. CNFP, which is a little bit newer, and then a number of vulnerability scanners that have network and transport layer identification modules, Nessus, and a whole bunch of others, Nessus obviously being one of the more popular ones. Right? Well, it's not a good idea to be going chasing after every tool and its techniques. I've concluded that it's best not to try to confound a specific set of algorithms. That it's best to just go ahead and disrupt any existing patterns.
Can you come? Not able to see that.
Oh, can you not see? I don't know if I won't move from the camera there. Well, they're recording me, and I know that I can't move around a bit. They told me I can't move around. All right, so the algorithm I put together, it does use some scrubbing. All right, in an identification, there are data points matching elements. All right, scrubbing is going to go ahead and reduce the number of data points that the fingerprinting tool has to work with. So the algorithm clears out any unnecessary values. All right, well, for the most part, these are operations that are good for 99% of the packets out there, not going to cause any problems. Clears out the IP type of service, DSCP, traffic class for the IPv6. Also clears out the IP explicit congestion notification, clears out the TCP urge flag and urge pointer. All right, reduce the number of data sets, give the tool a lot less to match up. Then go ahead and randomize anything that you can. So the algorithm does randomize the IP ID. There are algorithm analysis options going on, with techniques that are going out there that they're using to try to figure out who or what generated the IP ID. So randomize that, and you eliminate the ability to do an algorithm analysis. Another side effect of actually the scrubbing overall is you defeat reflection probes. A lot of software, particularly Nmap, will send data elements in the originating message looking for that to be reflected back. It's not common, but it does happen, and it helps identify some very specific types of operating systems out there. So if you randomize, if you're clearing things out and then you're randomizing, you are eliminating the usefulness of those reflection probes. That leaves just the IP TTL hop limit and the TCP options. They're really the remaining part of the packet at the layer 3 and layer 4 that's mutable or changeable. Right? So this is where outgoing normalization, packet normalization comes in. Now the algorithm to do this, first off we'll start with the IP time to live. There's some basic assumptions. Right? These assumptions are correct for 99% of the packets out there. The first assumption is that the packet had originally a well-known starting TTL. Okay? And that as the packet traversed the network, it would decrement only, okay? And that the packet would travel less than 32 hops. Okay? Now, using those assumptions, or operating on those assumptions, it backs into an original starting TTL to estimate the number of hops traveled. And then it then recalibrates the current TTL by subtracting those hops from a standard or standardized starting TTL of 255. So that's just a basic, kind of a step-by-step outline of it. This is a more logical approach. Okay? Starts with the lowest well-known TTL first. There are several exceptions to this normalization, which we'll talk about in a bit, that allows some mechanisms that are being used at layer 3 and layer 4 to do monitoring of the network, troubleshooting of the network performance. All right, some exceptions that we put in, or I put in, to make sure those still work. We'll talk about those in just a moment. This leaves us with normalizing the TCP options. Right? This algorithm also operates under some assumptions. There are only a few well-known options needed. Right? And then ultimately, order is unimportant. Now, with these assumptions, as the other, true for 99% of the packets out there. Now, I had an additional requirement that the values couldn't be changed. Right? I did not want to, in any way, degrade or disrupt the flow. I don't want to interfere with the socket and the flow that's going on. Now, using those assumptions, operating under that requirement, it reads the necessary values, discards the rest, and then rewrites the options in the proper order or the standardized order that I've chosen, and it knocks to the end to make sure that the byte boundaries are intact, the packet is placed in memory, is not disturbed, and any sort of calculations like checksum, the TCP checksum, does not break. These are the options that I selected, and the order for the standard: maximum segment size, or MSS, followed by window, followed by the selective ACK, and finally a MD5 option if present. So after processing, the TCP options look like so. Can you get that? Mm-hmm. So, putting it all together, making every packet look the same with ID guard, proof of concept. Okay. Now, it was important to select a good platform, to identify suitable hardware, make sure it was already modified by others. I didn't want to blaze the trail in that area, and that there was documentation available. I needed help. I needed to make sure that I could go get some and get some easily. So what I chose was the MikroTik router board line, or the RB450G. And then I identified a suitable operating system. I wanted to make sure it had an available base, and that this was important, a writable file system, so I could make quick changes. If you screw anything up, you want to make sure you can go back and not have to and change a small change and not have to reflash the entire router again and again and again. So open WRT. Now, the deploying to hardware was a long, arduous, difficult process. This is a brief summary. I actually have instructions that I put out on the project site that walk you through step by step. Right? I think it's a good set of instructions. You may disagree. If you have any comments on that, please let me know, because this is not an easy process necessarily, but the instructions help out quite a bit. There are source material though for this. The original sites, the instructions that I built were actually compiled from a whole lot of different sites, a lot of different sections of those sites, and there were instructions that were missing, instructions that were wrong. Right? So this is more or less to help you provide some context, maybe answer some questions, or you can email me. Right? But it is available if you want to repeat my work or go ahead and start from scratch. Are these the slides are being published? Okay. Important thing to keep in mind that I will go past some of these a little fast. Obviously, you couldn't write any of this down. It is available not only in the published slides, but also in the technical paper. So, important thing now is what worked. I know that I am, and I'm sure all of you are getting tired of those nosy bastards. First off, we're going to start with what didn't work so well. Okay? The type of service, TOS, DSCP, and the traffic class clearing, the ECN clearing, urge flag and urge pointer, the IP ID randomization, the do not fragment flag field discrepant. But it's important to note that I already knew going into this that it wasn't meant to be the solution. It was meant to make the solution work better. Reduce the number of data points. It was meant to make the normalization, well, make it better and make it to be much more effective. Right? So what worked? What really confused Nmap, what really confused these fingerprint tools was the TTL standardizing and the TCP options being standardized. Okay? The normalization. The end results. Windows 7, unprotected, because we obviously want to see what happens when you do this. But Windows 7, target, unprotected, is easily identified as a Microsoft Windows 7 host. Windows Server 2003, unprotected, as you would expect, looks like a Microsoft Windows 2003 host. Ubuntu Desktop 11.10, very specific here, always when you're collecting data. Unprotected is easily identified as a Linux host running the 2.6.x, 3.x kernel, and the Red Hat Enterprise Linux version 6. Unprotected is easily identified as Linux host running 2.6.x, 3.x kernel. Okay. No surprises, what we'd expect. Now, a Windows 7 target, protected by ID Guard, looks like an Allied Tellison Alliedware router. A Windows Server 2003 target, protected by ID Guard, looks like another Allied Tellison Alliedware router. The Ubuntu Desktop, this is where it gets weird. Well, it gets weirder. Okay. The Ubuntu Desktop, protected by ID Guard, looks like a Cisco router running iOS 12.x. Okay. You get further and further off base here. And then a Red Hat Enterprise Linux target running version 6, protected by ID Guard, looks like a host running embedded D-Link. Okay. So, fantastic results. There are some other effects, so it's important to keep in mind. They are there. Nmap. Reports, this is where it gets a also funky, and that is the Nmap reports a network distance, a negative number for that network distance. But the other fingerprinting tools, the nice thing is they're also equally confused. Xprobe 2, SynFP, Nessus's network and transport layer identification, also equally confused. And other tools like ping and traceroute, right? They are able to function normally. They are not in any way disrupted. Right? So there is one minor effect, the network distance, but other than that, it works great. But I can sit here and tell you how wonderful it is. I can show you. I think that's why we all kind of come out to see these things. So what I did earlier is I went ahead and removed ID guard. It is in this router here, loaded as a kernel module. This is the attacker in this case. I have a VM running. Or I did, should have. One machine I didn't bring up. Okay. Then we have on the other side, we have 4 targets, right? Potential targets. We'll find out in just a second what we have there. There's the host, and there's also 3 guest operating systems. Now, since it's not loaded, let's go ahead and do a scan. All right. We're doing a before and after. This will take a while. I've got 4 hosts running on their side there, 3 VMs, and 1 regular host operating system. It's doing what all fingerprinting tools do, sending a whole lot of TCP, UDP, and ICMP probes, collecting the responses, piling that in the fingerprint. It's going to match into the database. Okay. So we see some targets here. Right, this one here, identified as a Linux host, running that 2.6.x kernel. And another target here, identified running Microsoft Windows 7. All right. We have another target, identified running Microsoft Windows 2003. And a 4th target, identified as a Linux host running that 2.6.x kernel. So now, nope. Go ahead and load the module there. And scan it again. So we repeat the process. The machine is working very hard right now over there. Okay. We'll get that scan. Once again, probes running out, fingerprint, what there is of it is being collected, compiled, built into the database, or built into a fingerprint, which is going to then compare against the database. There we go. As you can see, the performance, really no difference. All right. So we see the first target looks like a host running an embedded D-Link. Second target looks like an Alloy Telson Alloy router. Third target looks like, and while they have a lot of Alloy Telson Alloy routers on that network. And we have a 4th target that looks like a Cisco router running iOS 12.x. So there you go. Now it's important, of course, to check to make sure the network still works. This would be great, but then not so great if everything was breaking, not working. Right? Let's go ahead and run a trace route. All these sorts of things should still work. Otherwise, this is no good. It's going. Well, that seems to take a little while. Time it out. So there we go with the first hop. And there we go. Second hop. All right. Trace route works fine. Let's go ahead and check out the web server that's over there. Make sure we can still browse to that page. Okay. There you go. Web browsing, not a problem. And how about that SSH session? Oh, still seems to be intact. All right, so there we go. Works great. Now, we do, though, have some challenges. This is not without challenges. First challenge is authorized activities. What about the hosts out there that are supposed to be doing scanning? Our hosts, the good guys. Okay. What about other methods of identification? Banners and direct query, your identification through layer 7. The first challenge, there's scanners out there. If you have something like a McAfee rogue system detector, supposed to be discovering new hosts out there, fingerprinting them, identifying them as possible threats, or management platforms. Those are really noisy, scanning the network back and forth, finding a little sheet that it has to take care of, all right? Manage those hosts. The resolution is ID guard can be loaded, telling it to exclude particular hosts from all transformations. Okay? So that challenge is overcome. Load ID guard to exclude the authorized hosts from all transformations, and that host, that scanner, that management platform can do its job. Then, of course, there are banners and direct query. Windows networking might be available, an application layer query is done, and the OS details are returned in the reply. The resolution is two phases to that answer there, two parts to that. Primitive network, those ports are generally not available. Verticals are generally not available outside, so that's not, a challenge there. Well, how about the internal network? Internal network, that is an issue. There remains to be an issue. What this means is that the application layer queries, their responses will also have to be normalized. It's something that I already have planned, so it will be dealt with. So for now, it will be a challenge, but ultimately, it won't be. That will be, of course, point 7. Right? So, challenge overcome. Then we have some concerns. Right? If there anyone out here who's really heavily into the network, probably are if you're coming to this talk, there are some concerns you might have. First off is, of course, fragmentation, upstream, downstream fragmentation. Then there is TTL attenuation, TTL special uses, some possible TCP options sensitivity, the link local routing protocols. There's some issues with that you might be concerned about. First concern, upstream fragmentation. The IP ID is randomized. At some point in time, as the packet traverses the network, maybe there's the do not fragment field is enabled. The router encounters it, sends back a message to the originating source. Host is confused. Right? Says, I didn't send a packet with that IP ID. I just keep sending that thing over and over and over again. Right? The resolution to that is pretty simple. ID guard clears the do not fragment field. There's a caveat to this, though. It will break MTU path discovery. I've not run across any problems with that. You may do so. If you do, you can always load that device as an exclusion to allow its traffic through. Right? A lot of equipment will do that. You can discover that the MTU, the maximum transmittable unit, upstream. Right? So you can exclude those, and you won't have any problems. Right? So, problem solved. Then there's downstream fragmentation. As the packet traverses the network, each fragment is given a different IP ID. And then, of course, the source host receiving it has a bunch of different parts that don't fit, don't go together. There's no longer association. Okay? So the destination can't reassemble that packet. Resolution, access switch placement. So that the IP ID is randomized before it encounters one of those routers. And as a precaution, ID guard excludes fragments from the IP ID transformation, just in case the host ends up doing the fragmentation. Right? So both of these together mean that the problem is solved. Then there, of course, is TTL attenuation. The packet travels more than 32 hops. Not all these hops are accounted for. The packet TTL is then continually extended by a little bit, and then in the worst case scenario, a routing loop occurs. Resolution to that is access switch placement. You put it before any sort of routing activity occurs, and at the end, switch after all the routing activity is over. You are now completely outside of any sort of routing activity altogether. It has no impact on the routing. It does not produce a routing loop. Okay? So problem solved. Then there are special uses for the TTL. This particular case, we're talking about trace route. Okay? The TTL, or the time to live, is recalibrated. TTL then never runs out at an intermediate hop. Doesn't run out, no intermediate hop reports, and the trace route fails. It just goes straight through to the destination. Right? The resolution, ID guard excludes ICMP echo requests from the TTL transformation. Just lets them through. And then ID guard excludes the UDP trace route range. Right? So it's covering your Windows trace route as well as your Unix and Linux trace route. Problem solved. Then there are the link local routing protocols. RIP packets have a TTL of 1. TTL, or time to live, of 255 is abnormal. Therefore, the packet is malformed. Resolution, ID guard excludes routing protocols from the TTL transformation. Another problem solved. And there's the concern of performance, or something is broken, poorly coded application, or who knows what else. I have not encountered any problems. I think ultimately, though, the concern should be that we are still allowing, broken or non-standard applications on our enterprise. There are a lot more concerns to be worrying about in this case than ID guard. You don't generally see issues, and I think that for me, a greater concern would be some of the more outdated, non-functional, not fully functional solutions that we have on the network. So we have fantastic results. What kind of benefits? I mean, this is great from a intellectual standpoint, but what kind of benefits are we going to see as far as protecting our network? ID guard shields the network from casual attackers. Casual attacker has a particular exploit that they have found on the internet. We're real excited, want to go use that exploit. They're not really going to find anything that matches that wonderful new exploit. They're not going to find that Windows target out there. They're going to find lots of Allied Telus and Alliedware routers. So, to be honest with you, how many exploits have you seen out there for Allied Telus and Alliedware routers? Right? So they're going to pass by those particular types of targets that they normally would focus on, normally launch that exploit at. Then there is the automated assault. A number of attackers will basically scan their selected network. They will attempt to identify a certain type of target because they have a matching exploit. They're going to sweep through there, and all they're going to find is a whole bunch of oddballs. Nothing that matches the exploit that they have, that they prepared to be used against it. Therefore, they're not going to launch that exploit. And then, of course, oblique threats. If there is a foothold, there are other means, let's say inside the network. They're going to scan the network. They're not going to find anything that they would prefer to pivot to. Right? They're going to look for a pivot to move out somewhere else. They're not going to find something that they're comfortable with, something that they have prepared for. Right? So it shields the network from all of these sorts of things. It also protects unmanaged, unpatched, and unhardened hosts. Because when it moves on, when the attacker moves on from these targets, many of these targets will be unmanaged, unpatched, and unhardened, so they will be passed by and left unscathed. Okay. It also helps defeat canned exploits. Exploits are great, but they often need context. The exploit needs to be tuned for the particular target. Even if the attacker has a general idea through other identification means what the operating system is on this target, the fact of the matter is we'll have difficulty tuning it for the target, increasing the likelihood that the exploit will be successful. Increasing the likelihood that the exploit will fail. Okay. So, fantastic results and great benefits. What's next? Open source router firmware. I actually might skip this and go straight to Linux-based switches. My next step is to put this on, don't tell Extreme. Extreme, because they have a Linux-based switch. They have Extreme XOS. It allows kernel modules to be loaded, so I'm going to try to sneak that on there, put that in a production environment for some trials. All right, and talk to some vendors, because this should be on a switch. This should be a feature not unlike what you see with DHCP snooping, IGMP snooping, a very basic protection for the network overall. Okay. Final thoughts to wrap this up. Accurate target identification is key to a successful attack. identification that is way too easy for an attacker to do. Let's change that with fingerprint prevention. I've proven that it can be done. Now we just need to make it happen. Proof of concept. Actually, there is a 0.5 already out there, but for Nullcon, I went ahead and created a 0.6. 0.6 has support for IPv6. Okay, this will be up later today. The SHA hash is there. That URL. There will be, once again, the slides available later to look that up if you don't get this now. Okay. And some links. We'll also get through that. The slides are being published as well as the technical paper. Really just a standard presentation. Thank you for having me. Any questions?
Yeah. Like if Windows 7, let us say, it is always detected as Allied Telesis router, and then Nmap database itself can be updated as data as Windows 7.
Well, what you're going to find is you're going to find dilution of the database and the identification to the point it becomes useless. If everything looks the same, then you defeat the purpose of fingerprinting. You're not actually fingerprinting anything.
No, the database itself can be updated as instead of Allied Telesis, he will make it as Windows 7.
The idea is to make everything look the same, so that even if they update it, they're updating all the entries to look the same again, because the idea is to have no distinguishing.
But we have 2-3 variations, right? Not
What's
all
that?
are same. Like in your protected mode, there were 2-3, right? One Cisco router, one Allied Telesis. 2-3 variations were.
That was because the systems were different.
The systems were different.
I mean, can that Nmap attackers can remap these systems to Windows 7, another Mac?
That wouldn't really solve the issue, right?
That would, yeah, it would dilute the database. It would also looking alike. It would do my work for me. Because
But on the other hand, you mentioned that you couldn't modify entirely what was left there, ECM and I think MSS. So you still had some proprietary menus left. So if this Nmap database is updated, let's say, make the primary identification as this right LSA plus this additional distributions which you weren't able to clear without breaking functionality, it can be updated to simply catch up with you.
The idea is to disrupt the pattern. So you're not necessarily trying to shift the pattern necessarily, have a separate pattern that they can lock onto. That just make everything look the same, so that it doesn't really matter. I mean, you're going to have some identifying marks, but the whole idea is to blur the lines and blur the lines and blur the lines. They're going to run out of stuff. They are very dependent on the TCP options. I would like to see what they do, and certainly if something like that happens, I would. Obviously, it's ongoing fight always between the attackers and defenders. I don't see it necessarily happening, but certainly it's something that can be addressed if it does.
One more question actually. Where do you foresee, so I understand that currently you have a working Linux kernel module which you can load to any embedded device or standard Linux server. Where do you see the deployment? Is this current, let's say, level of maturity? Where would you put this one in the network parameter given the kind of maturity that you have?
I originally was looking at it, the access switches. So the access switches for the buildings, everything before it goes into the aggregation switch. So it's at the very base of the network, so that you are not interfering with the routing, that sort of thing. You could also, of course, then do that in the data center, in the perimeter, anything where you have those after the endpoints.
Okay, so you are currently able to support all these access switches which will be running Linux kernel.
Anything that's going to run Linux
You
kernel.
don't have that many of those, right?
No, which is why it's a little tough. But the idea is to talk to vendors, and get this into the products. The code is becoming more agnostic, so that you can load that into different environments. In fact, I was just talking to someone about that yesterday.
So I'm actually looking of possibly loading this to every Linux server that may be running.
I wouldn't say the server, the switches.
Directly at the source.
Most implementations you're going to have a particular firmware image that you can go ahead and you can blast out there. As far as if you don't have the firmware image, if you are putting it in yourself, it could be difficult, which once again is why you want to try to go to the vendors to try to get them to do this. It's not going to be an easy road, but I'm willing to try it. I'm willing to fight that fight. Okay. Yeah.
The idea is really cool. It will be very helpful against massive force scan kind of stuff where they are scanning large number of machines. But when there is a targeted attack, what he said is really true. Like if we try to scan a machine and we get a result of area attack on a machine, then I can understand that maybe ID card is in place, so it is returning me a false positive, so I can assume it to be Windows.
No, well, not necessarily. I mean, especially on the Linux end of it, you might know it's Linux, but you don't know which Linux. If you're
Yes, yeah, but let me tell you, like, okay, that way we are able to at least differentiate whether it's Windows or Linux. But what's your take on, like collecting a similar set of signatures without disturbing the functionality and returning a random one every time, rather than trying to normalize everything? Like, I really get the idea, removing the data points and stuff. But still, why not? Like, what's your take on collecting similar signatures which do not affect the performance of the packet individually? I mean, which remains working state, and why not randomize your this thing every time so that Nmap returns a different result every time?
It was a thought of mine. It was a consideration. But then I got into a whole bunch of permutations that I was just, turning my head around and making it into Swiss cheese, because you're talking about maybe removing some, putting some options back. Yeah, I was thinking about moving things around in memory. I didn't want to screw with the kernel that way. I didn't want to, I wanted to have as little impact as possible, and not, for a nicer word, I didn't want to screw up the kernel any. I wanted to leave the kernel known as much as possible.
This solution is very good when we are talking about a massive scan. Like, you go to Shorten, and if you search for Windows, your thing won't appear in that search. But when I do a targeted attack on your machine, I can obviously deduce results from your ID card.
What you say then is, okay, maybe ID guard is there. It's a consideration now that this may be not a real Allied Telesim Allied router. It actually may be, Windows. That's human intelligence. That's what we do. We overcome things. It's going to be the challenge. That's where you run into with all the targeted attacks. It's not foolproof, but I think what it does is it makes them work harder, and that's what we want. That's what we look for. We try to make them work so hard that they get really, they're like, forget this, I'm out of here. You know what I mean? Move on to something else. Move on to someone else. Yeah.
Did you find a switch vendor or possibly a router vendor who would be already interested in implementing this?
I ran into someone just recently that was interested in doing this. Not in the big names. This was, but I think you have to start someplace. And I think that putting it into the extreme switches, I'm actually going to be requesting their SDK, which gives me like a VM, that sort of thing. They have a VM of their OS. I hope to start the conversation with them.
What's the name again, please?
Extreme.
Extreme.
I guess you can tell. I'm going to be telling them anyway real soon.
Yeah.
But yeah, because they have Linux. I mean, there's Cisco too. Cisco has their Linux-based switches, but I'm going to start with Extreme, they're more accessible. Yeah.
If any commercial vendor wants to implement this solution, what is the licensing requirement?
Right now it's open source. It's GPL
GPL.
3. Yeah.
GPL.
Yeah. Source code. Yeah, that is not like a compiled binary or anything like that. That is the source code, the POC that I have loaded up there. So you can see my code. You can see how messy it is. Actually, I commented the F out of it, but I'm just a very unconventional coder, so you'll get to see.
And when will it become included in the kernel main tree?
I would love that. That would be great. I always get excited when those kind of things happen.
So what's your expectation, like 2 years from now?
Well, the first thing to do is to get that into some switch, especially a commercial switch. I want to see this covering up further up the stack into the application layer. I want to also confuse Nessus, all the other tools, because that is a valid point. There's application layer authentication. I see that going away too.
And sorry for taking up with so many questions. And the lead pickup scanner, basically what these Windows Wireshark versions are dependent upon, did it respond similarly as Nmap?
PCAP, Wireshark, I'm not sure what your question is.
Yeah, well why should using, for example, Wireshark as a packet capture kind of front end, and then it's dependent on the split PCAP library.
Okay.
Various variations of it, which is a slight differences from Nmap.
Well, generally you're looking at the packet just as it's dissected right there on the screen. I mean, you just see the packet in all its glory. I don't think you're really, unless you're able to spot things with your eye, I don't think you notice anything different than Nmap. I mean, all my work is done in Wireshark. You're always peeking at the packet. Did it get moved around? Did it move around when it was supposed to? Did everything get standardized when it wasn't supposed to. So I just move things around, make the packet standard. It doesn't really do anything on, so I wouldn't see anything different in Wireshark. Well, hold on, there's one thing. One thing that I remember. Wireshark will complain. It will notice that it's not quite right. It will say that I think an intermediate router has, modified the packet. That's what it will say on the options.
Interesting. I was simply wondering why Wireshark wasn't included on your slide, because we had a mention of Nessus, you had an Nmap, so.
Well, because it's a lot of stuff all in one screen, and I just kind of did the little table, and I kind of moved to play the little musical chairs there, move things around. I did that because it was a little bit difficult on the eye to have a whole screenshot there of Wireshark. That's why. A lot of stuff. Opening and closing things. Yeah. Alright. You good?
But then, do you mean that Windows 7 will always be an allied device and Ubuntu 11.10 will always be a dealing thing, right?
I think it goes back to their points on the evolution. There'll be shifts. There'll be shifts, and I'll be keeping an eye on it, of course. So, yeah. We'll keep an eye. We'll see what happens.